Alright, this video is on solubility equilibrium. We'll be using this packet, and this will be the first video for this packet. There will be others. Definitely going to divide this video, or this packet. So, okay, so a little bit of background information in terms of things that are soluble and insoluble, right? For the longest time, we learned that a compound was either soluble or it was insoluble, and then we learned that, that was kind of not the whole truth, in that there's really no chemical that's purely insoluble. It's just that there are a lot that are what is referred to as slightly soluble. And so those ones that, our solubility rules would tell us are insoluble, and the likelihood, of us dissolving anything is relatively low. They're really slightly soluble compounds. Okay, they're not insoluble. And so that's what this discussion is all about today. So, as with any other equilibrium reaction, the extent to which a dissolution reaction or a dissolving reaction, occurs depends on the magnitude of the equilibrium constant. Of course, where magnitude means the size. So we're looking at how big is the value of K in this case. And this is going to be a different type of K. So up until this point, we've learned Kc and Kp, and this is going to be something different. This is referred to as Ksp, which the S and the P stand for solubility product. Okay, and so if this was my reaction, the dissolving of barium sulfate, or the ionizing, I guess I should say, of barium sulfate, and barium sulfate is a slightly soluble salt. Okay, it's on your solubility rules as being insoluble, but what that really means is that it's only slightly soluble. So we could write a K expression, except this time I'm going to call it a Ksp, okay? And that stands for solubility product. And the nice thing about this is you write it the same way, okay? You write it just like you would write a Kc expression. It's the same thing, same rules apply, just as a different subscript, okay? So a Ksp is going to be your products raised to their stoichiometric coefficients. And what's going to be interesting about your KSPs is every time we are talking about this idea of solubility equilibrium, your reactant is going to be a solid. And so if you can remember, solids are excluded from our equilibrium constant expression. So this is actually all there is to the writing of the KSP equation. Now, if we had coefficients out in front, like if this was a 2, of course I would have a squared on here, but that's not the case, for this reaction. We will see that later. So KSP values can actually just be looked up. There's a table of them in the back of your book. They could be quickly Googled for a huge list of substances. And so I looked this one up, and the KSP is 1.1 times 10 to the negative 10. Okay, whew, that is really small. And so this goes back to this kind of takeaway that how the extent to which this reaction occurs all depends on the magnitude of the equilibrium constant. Well, this is a very small equilibrium constant. And so what we know is that this thing is not very soluble in water. Now, we already knew that, okay? But what KSP will allow us to do is to compare the solubilities among compounds, so we could rank them based on their KSP value. So the bigger the KSP, the more soluble, the smaller the KSP, the less soluble, generally speaking. Okay, so that's what KSP allows us to do. And again, we're talking about things that are slightly soluble salts. Okay, so we're never going to see like sodium chloride. We're never going to see lithium nitrate, because those things are very soluble, and they don't establish an equilibrium. They're a only proceeding to the right type of reaction. So again, keep in mind these are your slightly soluble salts, or the ones that are referred to as being quote unquote insoluble, which we know is not the 100% correct way to explain that. Okay, so let's look at a problem. It says copper 1 bromide has a measured solubility of 2.0 times 10 to the negative 4th moles per liter at 25 degrees Celsius. Calculate its KSP. All right, so copper 1 bromide looks like this. So we know it has some solubility, and it's going to ionize into its ions, copper +1 in this case, and bromine -1. okay? So we'll go ahead and write a KSP expression. So the product, sorry. Again, in this case, they're both coefficients of 1. And what they tell me is that the solubility of this, okay, is 2 times 10 to the negative 4th molar. So I'm going to write that right here underneath the compound, because we're going to use this idea of creating a sequence, like we always do, to figure out what the concentration of each ion would be if this thing has a solubility of this, right? Well, this is a very easy one because these coefficients are all 1. So this would have a solubility, or a concentration, of 2 times 10 to the negative 4th, and so would the Br minus, okay? So again, to repeat, all I'm doing is writing a sequence with the fact that they told me that this was the solubility of the compound. Okay, just writing a sequence for my ions, and then I have these two numbers, so I can plug them in and calculate a KSP. So actually, it's just 2 times 10 to the negative 4th squared, right? Because it's the same, quantity. And so we get a value of 4 times 10 to the negative 8. And that should be the KSP value for this substance, okay? So that was a very simple one. I believe the next one is a little bit trickier. So if we flip over, number 2 says, calculate the KSP value for bismuth sulfide, Bi2S3, which has a solubility of 1 times 10 to the negative 15 moles per liter at 25 Celsius. Okay, so I'll go ahead and do my ionization reaction. So of course I get 2 of the bismuths and 3 of the sulfurs. So of course we know our KSP is going to be a little more involved. Okay, so I can go ahead and write that. KSP is going to be the concentration of the bismuth squared, right? And the concentration of the sulfur cubed. And I'm going to play the same game. I'm going to write a sequence with that molar solubility. They told me it was 1 times 10 to the negative 15. So that means I'm going to get double of this, because this is a 2. So this is going to be 2 times 10 to the negative 15. And then this is going to be triple of this one. So it's going to be 3 times 10 to the negative 15. And all of a sudden I have my 2 concentrations that I can plug into my KSP expression. I just have to be careful that I square and cube where necessary. It'd be easy here to, excuse me, to make a calculator error, only because we've got a lot of scientific notation and exponents and powers and stuff going on. But assuming we evaluate this correctly on the calculator, we get a very small number, something along the lines of 1.08 times 10 to the negative 73rd in terms of the KSP of this substance. Okay, so that's how you can calculate a KSP if they give you a molar solubility. It's pretty simple. And then the third problem is a little bit different. This third problem is kind of a nice lead-in to the next section that we're going to talk about. And so this one says the KSP value for copper 2 iodate is 1.4 times 10 to the negative 7. Calculate its solubility. So this is a reverse problem, right? Just in the first 2 we just did were they gave us molar solubility and asked us to find KSP. In this case, it's backwards. They gave us KSP and they're asking me to find molar solubility. So let's think about how we would do this. So we know this is going to ionize to some extent, right? If this is a +2, this guy's going to be a -1 because they gave me 2 of them. Okay, so I can write a KSP expression. Right, that's what my KSP expression would look like. And I have this number, right? They gave it to me, so this is the first time I'm not solving for it. But in this case, what we're looking for is, you know, what's the molar solubility of this? So we're going to have to introduce a variable here. And it's not super complicated. So if you think about it like this, the amount here, the molar solubility is going to be a 1 to 1 here and a 1 to 2 here. So what I'm going to do is call the concentration of copper plus 2 at equilibrium X, right? Because there's a 1, right? And I'm going to call this one a 2x. So this should kind of remind you of like an ice chart situation that we've just finished talking about. And then all I'm going to do is plug these into my expression. And then see, once I have a value of x, that value of x is going to be the same ratio as this whole compound's molar solubility. So concentration of the copper plus 2 ion is being represented by the quantity x. The concentration of the iodate ion is being represented by the quantity 2x. And the 2x is squared. Okay, so 2x squared, or 2x, the quantity squared, is 4x squared times x. Which, of course, we can combine and say that this is now 4x to the third. Okay, I want to find x, so I need to divide both sides by 4. And I think I did this all in one step, so I'm just going to leave it like this because I don't have a calculator with me. So I've divided both sides by 4 and gotten x cubed, right? But I don't want x cubed, I want x. So to get rid of that cubed, I have to take the cube root. This is where we have to make sure we have a calculator. So we're going to take the Ksp divided by 4, okay, because we got rid of the 4. And then I'm going to take the cube root on my calculator. That's going to give me x. Once we do that, x came out to be this. Okay, which is going to be a molar concentration. So I'm going to say that it's a molarity, right? It's not a Ksp. And so keeping in mind, we have to answer the question that they wanted the molar solubility of this whole compound. Well, so what we've solved for is x. You know, we could answer that the concentration of the copper plus 2 ion would be this. The concentration of the iodate ion would be twice this value. And then all we have to do is use my sequences, you know, that this is also a 1, to work our way back and say that, well, then this concentration, this molar solubility would have to be equal to that value. You could always check yourself. You could take this, you know, make it that, take this, double it, plug it in, and see if you get this value of Ksp, which in fact you will. So that's how you can kind of flip this problem around and work it in the other direction. And okay, so this next idea, and this is going to be the last idea in this video, is going to be kind of what we just talked about, which is their relative solubilities. So in that first, you know, we're looking right here, and in this first chart, it gives you, if you notice, it gives you 3 things that are all 1-to-1 situations. Silver iodide, copper 1 iodide, and then calcium sulfate. They're all 1-to-1 in their ions, and they give you the Ksp values. So I'm just going to do an example, which is actually just like what we just did. If we were to solve for the molar solubility when it's a 1-to-1 situation, okay, and I'm going to use, what did I use? Silver iodine, okay, for example. Well, I can think about the fact that this would ionize into silver plus and iodine minus, and I would know a Ksp. I looked this one up. Actually, just kidding, I didn't look this up. But that's okay. Oh no, it's in the chart. Duh, my gosh. 1.5 times 10 to the negative 16 is the Ksp that they gave me. Okay, so I can do what I just did and say, if I'm looking for this, the molar solubility of silver iodide, well, I know that I'm going to get some quantity of silver and the same quantity of iodine, right? Because it's all 1-to-1 in this case. So I can write my Ksp expression, which would be the concentration of the silver times the concentration of the iodine. I know my Ksp. It's 1.5 times 10 to the negative 16. This is representing x. This is being represented by x. So in this case, it's the Ksp, right, being equal to x squared. And so I would just take the square root, and that would give me the molar solubility in each of these cases, actually, because they're all 1-to-1. Okay, and in each case, you would be taking an x value times an x value, which would just give you an x squared, and you would take a square root to find your molar solubility. I did not do this math. You can do it on your calculator if you want to. But so if it's a 1-to-1 ion relationship, solving for molar solubility is very straightforward. However, if you flip, I'll leave that. And if we look at ones that aren't 1-to-1, it's a little bit more complicated, and it's that kind of discussion we just did in number 3. So if you look, and I'll do this one, the silver sulfide. Okay, so they gave me a KSP 1.6 times 10 to the negative 49. And, okay, so if I were to solve for molar solubility and I were to think about that this is going to give me 2 silvers and a sulfur ion, right? I'm looking for what this molar solubility is. I would represent this by x, this by 2x, right? If I were to write a KSP, it's going to be the concentration of the silver squared times the concentration of the sulfur to the first power. And then I would plug in what I'm letting them represent. So the KSP, which I know that value, but this would be the quantity 2x squared times the quantity x. And we're looking at that same kind of example problem that we did just a minute ago, where we ended up, taking the KSP, dividing it by 4, right? And then taking the cube root, which is going to give me that molar solubility. So you just have to be careful, and if your ions are, if it's not a 1-to-1, it just makes solving for molar solubility just a bit more complicated, because you end up with a exponent, which then of course makes my math just a little bit more difficult. So just keeping that in mind. But that's KSP, and that's molar solubility, and that's kind of the first part of this discussion on solubility equilibrium, and there are additional parts to come.